Okay, well, thanks, Randy, for the invite. Thanks for having me. Thanks for entertaining a slightly Trinity-focused talk today. I'm a fish biologist here in the Arcata office with NOAA Fisheries. Do quite a bit of work with the Trinity River Restoration Program, which has an office in Weaverville for those that aren't familiar. I want to just thank and give a shout out to the co-authors on this study, in particular Eli Sarian, who I know is there today, who's the lead author, and the other authors that you see there in front of you. It's a good team effort. Let's see. Let me pull up. Okay. Well, I'd just like to start off this talk just by mentioning that, the Trinity River has been used since time immemorial to support Native American tribes in both the Klamath and the Trinity Rivers. This is a map of the Trinity, pretty basic map here. Trinity Reservoir, there's about 24 miles long, I think, 2.4 million acre feet of storage, to give you an idea of its size. And these are photos of, on the left, Trinity Dam and Trinity Reservoir, and Trinity Hatchery, which is at the base of Lewiston Dam, which is the terminus of anadromous fish migration. So the objectives for the report, for the study, were to basically bring together a comprehensive data set, kind of everything we know about water temperatures in the Trinity River to date, evaluate the patterns between flow and temperature, evaluate the temperature on regulatory water temperature objectives, compliance, update conceptual models, and develop management recommendations. In terms of the methods, we basically separated time from going back to 1911. That's when the gauge at Lewiston was first installed. Separated the time periods into these 4 time periods you see here. The dam was built, Trinity Dam was built in 1963, so that's kind of a clear, that's when like full diversions to the Central Valley started. I put a little asterisk there next to the rod era because that's after 2000. That's kind of the inception of the Trinity River Restoration Program and kind of restoration of the last 2 decades. And so that's, definitely time period we wanted to focus on, because part of this is part of the adaptive management process, taking what we know, what we've learned, and then adjusting our management relative to what we've learned. Gathered a lot of data sets from all over, different tribes, agencies, used a variety of models to evaluate temperature effects on not only the river, but also did some work on frogs, insect generation time, things like that. So here's kind of a list of models here. RBM 10, Eli mentioned before, he's doing some work updating that. FIFAM is the foothill yellow-legged frog assessment model. SRH2D is a hydraulic model, and various other ones there. In terms of temperature, so we only have, I think there's like 5 or 6 years where we have a pre-dam data set for both flow and water temperature. So in order to generate all of the years of data, we built a model. It's a general additive mix model so that you can basically include autocorrelation structure and mixed effects, because when you're sampling, these water temperature data sets are not independent, right? Each measurement for, say, water temperature is related to the last one because of warming and cooling cycles. And that allowed us to generate an unimpaired flow and modeled unimpaired flow and temperature data set. What you're looking at there on the upper right is the measured leave 1 year out cross-validation of the model and these years that we have. So as you can see, it performed very well. So just to get into some of the results on your left here, I wonder if does my cursor come out on your screen? I don't know if it does. Anyway, on the far left there, the pre-dam era, you can see, it's typical Mediterranean climate, high flows in the winter and spring months, low flows in the summer. But on the far right, after implementation of the record of decision in 2000, the proportion of stream flow, we shifted a lot of that out of the winter into the spring and kind of have this higher flow in the summer. So really shifted the annual percentages of the timing of flows in the Trinity River. So what that did was a few things. So on the top there is the modeled before dams. We have 5 water year types, which is how we, on the Trinity River side, kind of generate the annual allocations based on 5 water year types. And a couple things to note in general for water temperature. You're looking at water temperature, like I said, before dams. The upper one there, you have a thermal maxima, almost always in August. And then with dams is in the middle there. And basically what that did is it flattened out. So there's less of a difference between the summer and the winter. And it also shifted. I'll show you some graphs later. We kind of shifted that thermal maxima to later in the year. And anyway, on the bottom there is a difference. So the biggest difference is in the summer, the river is a lot colder than it used to be. But also, as you can see, like January, February, March, it's warmer than it used to be in the winter. So that has a variety of effects, ecological effects on the entire river system. So if you look here, this is daily mean and max. What these arrows are pointing to right here on the top, as you go down the Lewiston gauge, this is far upriver is Lewiston up by the dam, all the way down to Wichipec, which is the mouth of the Klamath River. And notice these arrows I have pointed here. There's this kink right here. Again, I don't know if you can see my cursor or not, but there's a kink, and there should be this like normal warming pattern that you can see in the far left there. And that's basically interrupted because we let go these big restoration flows in like May, April and May. In the past, it's been like May and June. So that, it's basically interrupted the warming cycle throughout the year and made it colder in the spring than it would be otherwise. So what that's done here, the dark bars, the dark gray, is the optimal juvenile rearing temperature based on literature. It's like 13.5 degrees Celsius to 16.5 or so. And so if you look at like where my arrow is pointing right there, you can see how in April and May, the water temperatures are starting to warm up. And then there's the kind of the kink right there. And what's happened is we basically reduce the amount by letting go all this water, focusing our water, restoration flows on one time period in May. We basically reduced the amount of time that the river is within the optimal rearing temperature for juvenile salmonids. So on the far left, the 1978 to 1999, which is actually before restoration, we have 47% of days in June were within that optimal range, versus now in the in the post-rod era is 9%. So we made the water really a lot colder at not the time we want it to be a lot colder, is basically the take-home message there. And as you can imagine, this actually bears out in the rotary screw trap data. And the light gray is the post-rod period. These are fork lengths for Chinook salmon. This is from the juvenile synthesis report for the Trinity River Restoration Program. And basically, we modeled that in this paper, what would happen, and it actually bears out in the data. And the fish are actually smaller in the post-rod era than they were. So this is reservoir storage. Like I said, reservoir storage is about 2.4 million acre feet when Trinity Reservoir is full. These are just the actuals. You can just see like in the mid 2010, 2014, 15, reservoir got really low when we had really bad drought. It also got really low in 2021, which I'll talk about a little bit here. So a couple of things. Let's see. The top figure you're looking at. These are on the left. This main outlet works. That's the power outlet for Trinity Dam. That's generally where water comes out of the dam and into Lewiston Reservoir. And then the auxiliary outlet works on the right is way down below. And reclamation can forego power generation and use that in time periods when the reservoir gets low. So a couple of things just to notice here. This is storage on the x-axis. So as storage gets lower, water temperatures like at the outlet works and at the auxiliary works go up, and it's not linear. It goes up quickly because basically it's a giant pipe and you're entraining, water in like a big cone. So you're entraining water from not just one level. It's like getting water from multiple levels. And so when the water gets really warm at the surface, you start to entrain warm water when the reservoir is low. And then also you can see the two different lines, 1973, 1990, and 1998 to 2019. There's about a 1 degree temperature difference. So this lake is 440 feet deep. So at the deepest water of the lake, it's gone up about 1 degree Celsius, and we think that's due to climate change. And then on the bottom here, again, main outlet works and the auxiliary outlet works. You can just see in like 2014 and 15, when I was talking about, we had really warm waters at the release outlet. This is basically a similar graph, similar data for Trinity Reservoir. I would just point out, if you look in like September and October down there on your lower left, again, when you get these really low reservoir storages, we basically start to lose control of our ability to control temperature. And so water warms up really rapidly when the reservoir gets low. This is just a graph of basically salmonid survival versus egg survival versus temperature. And there's not a lot recently that's been done on coho. There's quite a lot that's been done more recently in the Central Valley on Chinook, but just on coho, I just want to point out that basically temperature drops very rapidly after 12 degrees Celsius. Coho salmon are one of the most intolerant to warm temperatures at the egg stage. And they're the highest survival where they have biggest alvin hatch, the biggest and whatnot, is around 4 to 5 degrees Celsius. And that's exactly where the water temperature would be in the Trinity River without dams. So I guess it's not rocket science, as they say, but the fish were adapted to what was there at the time their eggs were in the gravel. This is a graph of what happened in 2021 and 2020 for a comparison. The EOS, that acronym is end of September. So 2021, the graph in the red there, the end of September storage was 700,000 acre feet versus 2020, 1.3 million acre feet. So what happened was the river essentially never cooled off, and the thermal maxima was in November, which is what, like 3 or 4 months later than it should be. And this is really problematic for some onids that are adapted to temperatures declining seasonally and also as they swim upriver. In this case, in this year and also in past years, the water temperature actually warms up as the fish swim upriver because the dam acts like a big bathtub. And it's very problematic for fish. And this is what happened in that year. This is the survival of coho salmon eggs in Trinity River hatchery. And at those warm water temperatures in November, when these fish should be spawning, they had, this 12 degrees C here, you can see on the x-axis, almost 0% survival. So this is what the hatchery staff experienced in Trinity River hatchery, but almost certainly that happened in the river also. And actually, eggs in the gravel need more flow than eggs in the hatchery because the gravel actually reduces the velocity around the egg itself. So in terms of Klamath Basin talk, I tried to pick out some things here that we learned about the lower Klamath River, and particularly the effects of the Trinity on the lower Klamath River. So these are modeled with RBM10 flows. On the left, A are the flows, and then on the right are the changes in daily mean temperature. So as a lot of you know, there was a large fish kill in 2002, and since that time, managers have met and periodically prescribed flows for the lower Klamath River from the Trinity River in order to cool it off. And these are kind of the temperature effects from that. As you can see, right up by the dam by Douglas City, the Trinity, when you raise up the temperature, when you raise the flow, doesn't drop the temperature that much because the ambient warming hasn't warmed it up. But by the time you get down to Witchpeck, as you can see there, the effect of increasing flows on temperatures a lot stronger because temperatures are warmer. And then that gets washed out a little bit as you get down to the Klamath from mixing and then also from ambient air temperatures increasing. Also on the Trinity River, as a lot of you may know, on the Klamath side, in even years, the Yurok tribe has a ceremonial flow release, and then odd years, the Hoopa tribe has a ceremonial flow release from Trinity. And this is the effect of water temperatures from those ceremonial flow releases in the lower Klamath. So one thing that's important about this is that, it's important if we do flow releases just to make sure that it's not having an effect on Chinook salmon that are already in the river, because there are, at least from the preventative flow releases, there can be unintended consequences. So just to kind of summarize that stuff, you don't just get lower and lower flows the more flow you release from the Trinity River. It seems like around 1,500 CFS, which is about 1,000 CFS over the base flow release. Base flows in the summer have been about 450 CFS. So when you release about 1,000 more is when you kind of get into the maximum cooling effect on the lower Klamath River. Releasing much more than that doesn't do a whole lot. We do have some indications that maybe the RBM10 results are overly optimistic in terms of cooling. It overestimates the cooling. We think potentially due to RBM10 underestimating Klamath flows because not all of the smallest tributaries are included in RBM10. And I think Eli's got some work carved out for that to address that subject. Climate change, I'm sure a lot of people in the audience are familiar with climate. Most recent climate predictions not good. About a 90% decline in snow water equivalent by 2099 by 2100. Hardly be any snow left, unfortunately. And, you know, in terms of Trinity River storage, with the status quo operation we've had in the past, we have definitely lower storage and trouble maintaining storage. This is Trinity Reservoir inflow, and basically because of the snowpack, because of the reduced snowpack, the inflow into the reservoir really shifts into the winter. And there have been some reports that Trinity Reservoir is kind of potentially under threat for flooding issues if we get really big winters, really warm, big winters, that could be problematic for Trinity Reservoir in the future. So just to wrap things up here, you know, our flow releases have unnaturally reduced spring temperatures because we've shifted such a large proportion of our annual flows to the spring and with hardly any in the winter. We can't manipulate temperature. We don't have a temperature control device, so there's no way to manipulate temperature and flow without separately. Even at the bottom of Trinity Reservoir, again, about 440 feet deep, we have indications that the water has warmed down there by about 1 degree. And at storages less than 750,000 acre feet, adult salmonids and their eggs are really under threat from warm temperatures. And all of this is going to be exacerbated by climate change. And I'd just like to thank Reclamation for funding the work. The federal agencies provide a lot of their data. Hoopa and Yurok Tribe provided their input and their staff time, and others as well. The report is available there. There's a link to it. It's on the Trinity River Restoration Program website. We do have a bunch of like management recommendations and whatnot. I'm not going to go over those. I have those at the end of the slide if people are interested in those, but they're in the report. So that's all I have. I don't know how I did on time there either. I wasn't watching.
Fine. Any questions from the audience? Yes. Liam.
Yeah, Liam Tank, USGS. Just curious if anybody in the room is speak to juvenile coho out-migration numbers for the last 20 years from Trinity.
Out-migration numbers for coho, unfortunately, we don't have, you know, the traps aren't really good at, we have rotary screw traps, and they're not the greatest at catching, especially like yearling coho, because they can, you know, swim around them. So I would say the data set for juvenile outmigrants and coho over the last 20 years is incomplete. You know, we have raw catch from the traps, but it's you know, it's not the greatest to really say anything with. In terms of adult returns, we do have that, and it's hasn't been, the trend has not been good over the last 20 years.
Lyra Cressy, Salmon River Restoration Council. Looking at your seasonal maximums, even though they're significantly later than they should be, it seems like the Trinity River stays so much colder than the Klamath and other Klamath tribs in general, that I wonder if, you know, say your seasonal maximum there that you were showing on the graph in November looked like it's about 12 degrees C. Like, I wonder how different that is from a natural maximum in November on, say, the Salmon River. Like, would we see anything? Well, like, actually,
Well, I don't have the Salmon River data in front of me here, but I know if you look at basically almost all the unimpaired streams look something akin to that top graph, where once it starts cooling in August for a lot of our unimpaired streams around here, the temperatures cool off. Now, whether they're cooling off to down to 12 degrees or whatever, I don't know. But for almost all unimpaired streams, the thermal maxima is in August, because that's when air temperature and sun aspect and all that is affecting that.
I guess I didn't mean the maximum. I just meant that like with the normal temperature in November in an unimpaired stream, it would be on a downward trend, unlike what you're seeing in the Trinity, but I wonder if it would be that much different.
Yeah, well,
It's like
I mean, a couple.
Trend is different, but your maximum is so low compared to,
Yeah, and now that's
unimpaired.
that's right at Lewiston, which is at the base of the dam. So that doesn't show all those stations downriver, which have much higher temperature. As I just point to this graph on the bottom here. If you look in basically October, November, you can see there it's warmer. We made the river warmer than it was.
Yeah.
And in terms of some of your the smaller the streams that are smaller are going to cool off faster. There's just less thermal inertia there. But again, just in terms of coho, if you look at coho, and it's why some of these streams have coho spawn, much later, because it needs to be quite a bit colder for their eggs to survive. But again, if it's over about 12 degrees Celsius for coho eggs, not in the females themselves in the river, but once the eggs are in the river, it's an oxygen exchange thing, and the oxygen across the membrane, there's basically, if it's over 12 degrees, their survival is going to be like close to zero.
Any other questions? All right, Seth, thank you very much.
Okay, thank you.